So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Welcome back. We are now in lab 2, and first of all, the very first task I want you guys to make sure that you are doing is that, well, form your group. I know it's a little bit hard for this social distancing period of time that you cannot meet you cannot meet in person, but you know, we have Zoom, we have, well, other technologies like Google's or Facebook, so it's still possible to connect with each other, and it's like also give you a very good contact to find reasons to have some virtual social events with your friends. So the very first thing that I want you to do is that make sure that you form your group, and by default I would like to see groups in 2, but you know, like some of you saying that, well, I just want to be socially isolated, fine. It's okay to have just 1. And some of you saying about like, yeah, I'm this person. Well, these 2 other persons are inseparable, so we want to be together. Okay, 3 is okay. However, because we are not making burgers, so I don't think we need 5 or 4 this kind of group. So just make sure that, well, you want to make sure that your size of the group is around like 2 or 3, and even 1 is okay. And in fact, sometimes just having 1 person is probably making your life making life easier, because you don't have to negotiate, you don't have to find other people's bug, and you know what exactly that you are doing. So but and actually, like, if working with another person is more challenging, and if you have 2 more persons to work with, it's going to be even more challenging. So I would say, like, knowing how to collaborate with other people, that's a good practice, and 2 is enough. But you know, having more is probably not too helpful, and in fact, it probably would hurt. So here is the highlight of lab 2. So in lab 2, you will be implementing data path elements for a single cycle processor. So data path elements, meaning those elements that will, your data, just the data will flow through, not the control signals. And in your CSE140, which some of you just took last quarter, you should know the distinction between data path and control path. And here we are just asking about the data path. And we are implementing a single cycle processor. And if you don't know what single cycle processor, for now, that's okay. But you know, in a textbook, there's a chapter 4. You will have a reading quiz on chapter 4 pretty soon. And by then, you should be figuring out that a single cycle processor, meaning that it's a processor that we finish everything that we need to do for an instruction within just a cycle. And no matter what that instruction is, every instruction would take exactly 1 cycle. So that's a single cycle processor. And you might think, wow, I have to do everything described in that is described in a textbook. The answer is no, because in this class, we are going to give you ALU, we are going to give you a data memory module and the instruction memory module. So those are given, and we are going to give you the instructions, so you don't even need to compile the code. And you just need to implement the rest. And the very first thing that I want you to figure out is that what's the schematic of your processor? What do you need to do? And what are the elements required for a single cycle processor? And how to test each component and how to connect them together. So before we can do that, first of all, you have to know what we really want an instruction to do and how a processor needs to deal how the processor needs to do to deal with an instruction. So here's a step. So first of all, we have to fetch the instruction. So can some of you tell me that if I want to fetch the instruction, what component do we need to that happen? Can some of you raise your hand? If you don't, then I will probably unmute some of you and ask you guys to answer me, what is that? So which element, which data path element that you know of, we will be using in fetch instruction? We just mentioned it in the previous slides, give you a hint. Okay, if not, let me see. Giovanni, what do you think? Hello, what do you think? What do you think we need?
The counter.
For instruction fetch, what do we need?
A counter to go to the next instruction.
Okay, you need a program counter and go to where?
To the next instruction.
Yeah, where is the next instruction?
In 4 bytes.
Where? Yeah, but where we put that instruction in the hardware?
In the register file.
No, like see, how many stuff are we have here? Which one? We have the program counter, where it get the instruction from.
The memory.
Yeah, we need to access the instruction memory, right? So that's the first thing to do. And after we are done with the instruction memory, we need to decode the instruction, and we put the operands in registers. So you need the registers in your processor. And when you need to execute an instruction, you need ALUs. And so you need ALUs, and the ALU will interact with your register file. And after you are done with the ALU operation, if it's a data memory access instruction, then you need to use the ALU result to access the data memory. And finally, you can write the result back to the target register. So that's the life cycle of an instruction. And then you advance to the next PC, right? That's the life cycle of an instruction. So if I want to build the processor, right? And the very first thing that I need to do is instruction fetch, and it should be fetching from the instruction memory and according to the content of the PC. So your data path elements, first of all, you need an instruction memory. And the instruction memory itself contains all the instructions that we have. And the PC would tell us where to get that instruction. And again, after you fetch that instruction, by default, the next PC would be PC plus 4 in MIPS. So you need an adder to advance the PC like this, right? So that's the data path element that we need for instruction fetch part. And then the next thing that we need to do is to decode those instructions and fetch those, prepare those operands from the register file and make them the input of your ALU. So it requires to figure out the type of the format of your instruction. So for our type instruction, which we briefly mentioned in the class, it has 6-bit opcode, 5 bits for RS, RT, and RD. These are the registers for source and target. And be careful about the difference between the instruction encoding and the human readable expression. In human readable expression, we put the RD, which is your destination register first. However, when we encode those instructions, we put RD in the middle, well, behind RS and RT. So there, be very, very careful about this when you try to compare your design with the given code, because the RD is located at a different place as you can as the human readable representation. And the reason why we only need 5 bits is because in MIPS instruction set architecture, we have 32 registers, and to encode the number of these 32 registers, we only need 5 bits. So for R-type instruction, and because we have 50 opcode, 50 different operations to support, and we have 6 bits of opcode, because for 50 instructions, you only need 6 bits to encode those instruction names. And for shift, because in MIPS instruction set architecture, you can only have 32-bit wide numbers in the register. So again, and if you can shift, you can at most like shift the numbers by 31 bit. So the shift amount is only put at like 5 bits. And finally, there are 6 bits of function code that describes the slight difference in E-type instruction, or say the different function of this R-type instructions. And for R-type instruction, it's called R-type because they have 3 registers, because all the operands are registers, and a lot of them, and and most of them are like arithmetic instructions or logical instructions. And there are also 2 register R-type instructions like shift left or shift right. And for shift left and shift right, they only have 2 register inputs. However, they do use the shift amounts. And be careful about the encoding of this R-type instructions, and you should be able to find the encoding through a card in your textbook or the appendix in your in your textbook. And there's also 1 register R-type instruction called jump and return, which we talk about in the lecture as well. And again, for R-type instruction, the high-level guidance is that every operand in R-type instruction is a register. And for the second type of instruction is called I-type instruction, and it's called I-type because there's an immediate field. And for the immediate field, it says up to 16 bits. So if you have a number that's bigger than like 2 to the 16, it's impossible to encode it in I-type instruction. And its format is like this. And again, because it doesn't have an RD, so it's just RS and RT. But be careful about that, right? We put RT first, but he as a destination. However, RT is actually encoded later. So in the human readable representation, we always put the destination first, but in the machine encoding, the destination is actually coming later towards the least significant bit. And the most, and in addition to the immediate, add immediate, arithmetic immediate, or logical immediate, or the branch instructions, another big category of R-type instruction is the memory access instruction, and it also uses the immediate field to encode its offset that is also 60-bit wide. So this is the I-type instruction, and again for I-type instruction, it has a 16-bit immediate field, and for the J-type instruction, it's 26-bit for the immediate. And we have jump and link and the jump. And through the lecture today, you should be very familiar with the jump instruction. And again, for every instruction, we have 6-bit of opcode. And this, so right now, we know this is an instruction format. So we get an instruction with 32-bit from the instruction memory. And right now, this is the instruction format we have. And we have 6 bits of the opcode. And this opcode is going to be used by the control path to set the control signals correctly. So they are not going to the data path. So for lab 2, we temporarily ignore that. However, for the rest of the 26 bits in the process in the instruction, we will use them for the lab. And remember, for R-type instruction, its destination is in RD, and for I-type instruction, its destination is in RT. So the only thing that are common for these two instructions is that the first, these two types of instruction is that the first register input is actually encoded in the 30, what's that? 25th to 20 bits. So you should use the 25th to 21st bits as the input for the first register as your register file input. And now, the second input for this instruction, for R-type instruction, is clearly coming from the 20 to 16. However, for I-type instruction, it doesn't have that, right? But it's okay if you just read it. So we still put that in the, we still put 20 to 16 as the input for read rec 2. However, later on, we have to ignore their output because the output of read data 2 for the I-type instruction because we are not actually using them. And for the write, that's the target. And for the target, if you look at R-type is in RD, which means it's in 15 and 10 to 10, 15 to no, 15 to, and for I-type instruction is equal to 20 to 16 bits. So right now the question is that the issue is that you have to select between 20 to 16 and 15 to 10, depending on its R-type or I-type for your write rec. So and as you probably previously learned in CSE140. To select between two different inputs, you need a mux. So you need a mux selecting between 20 to 16 or 15 to 11 as your input for the write rec. So that's the mux part. And oops. Okay. Okay, so now we have the register file output by using this inputs, right? So the next thing to do is that, okay, why we need this register file output? Because we want to fit them as the input of LUs, right? And for the LU inputs, right, depending on what instruction it is, right, it comes from different places. And as we said, for R-type instructions, we are going to use both of the read data. However, for I-type instruction, we are only going to use one of them. And the other one comes from the immediate field, which is the 15 to 0. But another thing that you have to be really careful about is that for ALU, it only accepts a 32-bit input. And if we don't connect it with a 32-bit number, a lot of them will become don't care or floating, so which will make your design problematic. So what we really have to do, so we have to additionally put this sign extension unit that extends the top most significant bit of your encoded immediate field with the topmost bit that's current with the rest of the 16 bits. So saying that if you have an immediate number, 16-bit immediate number leading with a 1, then the rest of the 32-bit number on the most significant bit between your bit number 31st to 16, they should be set to 1. However, if your most significant bit of that immediate field is 0, the rest of it should be 0 as the input. So that's why you need a mux here again, because for I-type, we want the input from here. For R-type, we want the input from here. And after we are done with the LU, we will use the LU result for potentially for two different purposes. If it's a data access instruction, we will use that as the input of your data memory address. And if not, then we are, and if you are using that as a data input address, then the second read result will become the content for your write data. And if you are not using the data memory, then you are using the LU result as your register, as the outcome of your computation. So you also need a mux here to select if I should be using the data memory or I should be using the LU outcome to put back to your register file. So that's the whole data path components, all the data path components you want. And each of the data path components, you may need control signals that you have to set later on. And I just put them on. And right now you don't have to connect it because we don't have the control unit. But if you have this control signal in mind, you will, it's good in a way that you could leave, I would say, like a hook in your module, so that later on you just put them into the right, just plug the right signal in there correspondingly. And here's what you need to do. So as I said, we gave you the instruction memory, we gave you the LU, we gave you the data memory. So you just need to implement the red parts. Well, so I misdraw the LU. We actually gave you the LU, so you don't have to implement the LU. So you only need to implement the red parts, which is mainly the register file and a few muxes and a PC+4. And you don't have to implement the LU. You don't have to implement the data memory. You don't have to implement the instruction memory. We have done that for you. So thinking about that, your lab 2 is just a few muxes and a register file, PC+4, and connect them together. That's what you need to do for lab 2. You don't have to do the instruction memory. You don't have to do the LU. You don't have to do the data memory. We provide them. And here's the interface for what we provided. So for the data instruction memory, it's a module with a clock input, with address input for data output and reset. And remember, right, this comes from your PC. And this is a clock signal that you should be able to generate, and you should receive that as your module. And the output, the data output is actually the instructions, the instruction that you are going to execute, and we should fit into we should fit them as the input of a register file. And it's your duty to design the register file. And the LU, here's the interface. So for the LU, it provides quite a few different functions. So we have an input of function in to define their functions, and it would implement most of the LU functions we need for MIPS instructions, and you don't have to deal with it. So in this lab, it's just you just later on just need to make sure that you put the right function code, and the LU would generate the result as you want it. And but what you really need to fit into the data path is the 32-bit register input. The register output or the extended immediate values as the input for the LU, and it would output a 32-bit number. And for the data memory, it's more complicated, but and you will get the rest of the signal later on from the module. And the reason why we have this many signal is because in the processor that you are going to implement, we said that you can do simple input output, and we use the serial in, serial out to allow the user to input and see the output. And so that's why we have this additional signals to deal with that. But don't worry about that because later on we will tell you what to do with that. So right now, just accept the fact and just use the data memory. And but what you need to do is that make sure that you connect the address in and the right data in, and connect the read data out to the write back logic that we need. And finally, what you need to do, right? This is the main part. This is the very important part that you need to do. You need to design a register file, and the register file should contain at least you should contain at least like this input, right? And a few design questions that I want to ask you, but not right now. You probably can answer it through your interview. Is that, do we need to have a clock? Why or why not? And you probably also wanted to support reset, so that in the very beginning of your processor, you can set everything to 0. And again, MIPS instruction set architecture, all the registers, they are general purpose, except for one, that is the zeros register. So make sure you have a test case showing that the zeros register always give you 0, no matter what you do with it. So the most important thing, in lab 2, you and your group member don't have to write any report. There's no written report anymore after lab 1. And all you need to do is that during our office hours, show us it's working, and show us you wrote your processor.b, show us you have your register file.b ready, and demonstrate it works. And to demonstrate how it works, you need to show your own test bench. You need to design a test bench. You need to design your test cases that covers everything. And if your test case is insufficient, our TAs or tutors might call you on the spot and ask you to implement that too. And you have to do interview again with us. So if you want to save your time, try to make your test bench as complete as possible. And you need to show us a schematic. But again, similar to what we asked you to do in lab 1, as this course is not CSE140, and I don't think you are going to make a better, well, it's really hard to make a more clear draw than just use the RTL viewer in the Quartus 2. So you just need to show us the schematics through the Quartus tools, and we might ask you why you have this elements here and why this is connected here. Why do you think your data path is connecting correctly? So this is what you need to. This is all what you do. What do you need to do? And some of you ask you, do you receive our grades at the interview? The answer is yes. So and for this class, the interview is a binary. So as I said, we will tell you if you pass the lab or not. So it's your grades is either 0 or 100, or say like incomplete, and then we will give you 50. So there are only 3 different levels of grades you will get. And if you don't have the previous lab finish, we won't allow you to interview for the next lab. And can you interview again? The answer is yes, you can interview again. And please ask question by raising your hand, because I cannot it's really hard for me to see those chats, and sometimes I may misinterpret your question. So this is what all you need to do for interview. Just tell us the things. And the next lecture of lab 3 is going to be on lab 3. It's going to be next Wednesday, so we don't have lab lecture next Monday. And the lab 1 would do this Friday, lab 2 would do next Friday. So starting from today, you should have roughly about 10 days on lab 2. And if you are done with lab 1, go ahead, start doing lab 2. And we will try to pull the content of lab 3 as early as possible. So in case, because lab 2, I don't think it's too difficult, given that we already gave you all the modules, well, most of the important, most difficult modules to implement. So you don't have to implement the LU, don't have to implement the instruction memory, you don't even need to implement the data memory, right? So thinking about like how easy is this? So we are actually making your life in CSE141L relatively easy by providing you a lot of modules. So if you have friends who is in CSE141 but not in 141L, tell them it's actually not as difficult as they could imagine. And if you take it in a later quarter, I'm sure, because it's a quarter, it's 10 weeks, people would have higher expectation than what they wanted to do in 141 Lab. So that's another thing that I really want to let you know, that if you are taking CSE 141 this summer session with me, highly advised to take the lab with me. Okay, so questions? Okay.
Professor,
Yes.
is it possible that we can go over lab 1? I'm kind of not sure.
So
like,
if you want to do it, if you want to go over lab 1, you should use our office hour.
Okay.
Because I
so-
think everyone is in different stage of that. And the lab 1, the only thing I can, did you try to follow the document that we put online?
Yeah, it's instructions are kind of not clear to me, or like maybe my like understanding is not
I was,
enough.
yeah, so I would say like because it seems very clear to me. And if you ask me right now, I would just ask you to do exactly the same thing. And I'm just showing you exactly the same thing that's in the document. So if you really want to get help, we have office hour tonight.
Okay, sure.
Okay, other questions? Okay, if not, I will see you tomorrow in the lab lecture, in a lecture.